Hello, welcome to Chapter A on the solar system. In part one of this video, we'll be looking at the formation of the solar system. So this chapter and the ones that follow it are a little bit different. They're not in the textbook. So I've labeled the chapters with letters. The astronomy chapters that we're going to be covering will be chapter A, B, C, D, and E, since there are no chapter numbers that correspond to the textbook. So for all of this material, you're just going to use these notes, the lecture notes that are posted on Cougar Courses, or this video lecture. That all the material that you'll need for the homework and for the quizzes will be found in this lecture. So this chapter A on the solar system is broken up into four parts. Part one, which we will do right now, is on the formation of the solar system and extrasolar planets. Part two is on the inner solar system. Part three, the outer solar system. And part four is on what is called space debris, and that is comets, asteroids, and meteorites. So let's start with the basics. What is the solar system? Well, the solar system is the sun and all of the celestial bodies that orbit it. So this includes the planets, their moons, a different classification of planet called dwarf planets, and also things like asteroids, comets, and meteors. And we'll be looking at all of these things in more detail in the various parts of this chapter. So this picture here gives us sort of an overview of what we're going to be dealing with. Over here on the left is shown our sun, and then here are the 8 major planets of our solar system in order. Mercury is the smallest and also closest to the sun, followed by Venus. Here's our Earth, here's Mars, and here's Jupiter, the king of the planets, the largest one, Saturn, and then Uranus and Neptune. And then there are dwarf planets such as Pluto and various others that we'll be talking about. This picture here is certainly not drawn to scale in terms of distances, but it does give us the correct scale and sizes, so you get an idea of how large the sun is compared to, for example, our Earth. This is another diagram that shows the relative sizes of the planets compared to the sun. So this is the sun in the background here, and you can see our tiny little Earth here is dwarfed by our sun. In fact, you could fit 100 Earths across the diameter of the sun, and you could fit 1 million Earths inside of the volume of the sun. So our sun is obviously enormous compared to all the planets that orbit it. And also you get a sense for the size of Earth to some of the other planets, especially the larger planets such as Jupiter, Saturn, Uranus, and Neptune. By the way, we are starting out, talking about the solar system here. We will talk about the sun in a later chapter, in chapter B, which is on the stars. We have the first part of that lecture will be just on the sun. So we will not talk about the sun in this chapter on the solar system. One of the main ideas of this part of the lecture is, where did our solar system come from? This is the origin or the formation of our solar system. And the scientific theory that explains it is called the Solar Nebula Theory. Now remember, the word theory in science doesn't mean a hunch or a hypothesis. Theory here means this is the highest level of confidence and understanding that we can have in science. For example, we learned earlier about the theory of gravity. And so, be careful, again, when we see the word theory here, in science, a theory, it has to be backed up by all the available physical evidence. And what I'm going to present to you in this lecture and in the ones that follow is a lot of physical evidence that allows us to build these theories that describe the origins of things like our planet Earth, our solar system, and even the entire universe as a whole. So the idea for where our solar system came from is called the Solar Nebula Theory. And first of all, a little bit of definition here. The word nebula means a giant cloud of gas and dust. So in this diagram here, this big gas and dust cloud represents a nebula. So the solar nebula theory is the modern theory of planet and solar system formation. It explains basically how our solar system formed and how we got here. The idea is that planets form at the same time from the same cloud as the star. So what this tells us is that our sun and all of the planets in our solar system all form together from the same nebula of gas and dust. And evidence tells us that the sun and all the planets in our solar system formed about 4.5 billion years ago. So that is actually the age not only of our solar system, but this is also the age of our Earth. So the way the solar nebula theory basically explains the formation of the solar system is we start with a rotating cloud of gas and dust. And because of the enormous size and mass of this dust cloud, there's a lot of gravity. And that gravity is causing this thing to contract, to shrink. Remember, gravity is an attractive force. So this cloud is going to shrink under its own weight over time. What happens here is as it shrinks, it has to spin faster. And this is something that we didn't cover in our lectures earlier on physics, but there's something called conservation of angular momentum. If you think about a figure skater that spins around, and as she or he pulls in their arms to their body, they spin faster. And that's because angular momentum has to be conserved. So what happens here with this gas cloud, as it starts to contract and get smaller, it spins faster. Now, something interesting happens. As it spins faster, it has to start to flatten into a disk. And we see this the same physics at work here if we ever watch somebody making pizza. If you go to a pizza restaurant and you see how they take the ball of dough and they flip it up in the air and they spin it, and they keep spinning it faster and faster and faster, and what happens? Well, that ball of dough flattens out to form a disk. So the same kind of physics is at work here, just on a cosmic scale here for this gas cloud. So it starts to flatten, and in the center of this flattening disk of gas and dust, the density and the temperature gets very large, and this is where the sun or a star actually forms, is right in the middle. So here you can see it in this picture here. This is the newly formed sun, or we're going to see other examples where this happens elsewhere in the universe, and this is just another star. Around the sun or star is the remaining debris that's left over from this disk of gas and dust, and it starts to separate and clump and form rings of material, and we'll see that these eventually form the planets. So what kind of evidence do we have that supports this theory? Well, it turns out there is quite a bit. In fact, the evidence is overwhelming. And one of the hugest pieces of evidence here is observations of other new solar systems forming right before our eyes around newly forming stars. So we're going to look at that next. This is a nice graphic here that these are diagrams that show how this process works in a little bit more detail. So again, these are the steps of the solar nebula theory on the formation of our solar system. So up here in the corner here, this is the solar nebula, which is a rotating gas and dust cloud. And as it spins faster and faster, it starts to flatten out into a disk. That's shown here in step B. And then in step C, we see the star forming in the center of the disk, and around it you can see that the clumps in this disk start to form rings of material, and those rings then start to condense into chunks of material called planetesimals. These are like tiny little rock-like planets. They're really not a planet yet per se, it's just debris. And this debris starts to come together to eventually form planets, and then over time the rest of the debris starts to clear away, leaving the planets orbiting the star, or in this case our sun. So one example that I'll show you right here is really interesting. We saw in the last slide this animation or drawing showing the steps in solar system formation. Well, look, this picture here is an actual radio telescope image. So remember, a radio telescope we talked about earlier is basically, it's a telescope dish that collects radio waves, and by connecting these telescopes together we can get really high detailed, high resolution images of the universe in radio light or radio waves. So this is a radio image of a new forming star. This star is only about 1 million years old, which sounds old to you and me, but in terms of cosmic time, that is a recent event. That's like yesterday in terms of the age of the universe. So this is a newly forming star in the center here. It's called HL Tauri. It's in the constellation of Taurus. And what's interesting about this image, of course, is that not only is the star in the center, but you can see distinct rings of material around the star, just as is shown in these drawings here. So this is physical evidence that supports the solar hypothesis, or solar nebula theory, I should say. These are some more of the same, basically. These are radio telescope images of what they call protoplanetary disks. And again, this word protoplanetary just means this is the early stage of a planet's formation. A protoplanet is kind of like a prototype. It's an early model or an early addition of what will become a planet. And so in all these pictures here, again, these are actual images from radio telescopes showing basically stars forming, and around the stars are rings of debris that are going to eventually form planets. This is some more physical evidence for the solar nebula theory. This is, again, kind of showing the idea of planets forming around other stars occurring right now at different places in our galaxy. So these are images taken from the Hubble Space Telescope, and this is in the Orion Nebula. So remember, the word nebula means a gas and dust cloud. So you can see the cloud of gas and dust in these images here. But within these gas and dust clouds are newly forming stars. And we'll learn more details about how stars form later. But basically, this gas and dust in the nebula is raw material for a new batch of stars. And what's significant about these images is that if you look at these pictures of the stars forming, they all have regions of dust and gas around the star, these dust and gas disks. Here are some close-up pictures of some of them here. And almost every star that they see that's forming is accompanied by one of these gas and dust disks around it. So this is more evidence that supports the idea of how solar systems actually form. And it also tells us that whenever stars form, it appears that planets are also going to form with the star. And that is huge and important news, because it tells us that planets are probably extremely common in the universe. In fact, there are probably many more planets than there are stars, and we'll talk about that shortly. So this idea of the solar nebula theory, we've already seen some evidence of star formation with disks and rings of material around it that we think are, or at least are very confident that someday those rings will coalesce into individual planets, just like they did in our solar system. But it would also be nice to actually find some of these planets that have already formed. And so that's what we're going to talk about next. And a planet that orbits another star outside of our sun is called an extrasolar planet. That means outside of our solar system. So there are three main methods of finding extrasolar planets, and we're going to look at these, each of these in a little bit of detail here, because it's very interesting to see the results of these. Surprisingly, the least productive method of finding extrasolar planets is direct observation. So, you would think that the way to find an extrasolar planet would be to take one of these really powerful telescopes, like the Hubble Space Telescope or the big Keck telescopes, the largest and most powerful telescopes in the world, and point them at stars and see if we can look for planets. Well, it's possible on paper and in theory, but it's very difficult. The reason is the stars are extremely far away. We're going to learn about the distances to the stars, but the closest star to our solar system is about 25 trillion miles. And so that is just an enormously vast distance. And that's the closest star. Most of the stars are much, much farther than that. So the problem is at that distance, the planets are very close to the star in the sky, and the bright glare of the host star almost always blinds the telescope to find these faint little planets that are orbiting it. However, we have had some success in finding extrasolar planets, and around 40 planets have been directly observed, and I'll be showing some of those to you shortly. Two other methods that are much more productive are called the transit method and the Doppler shift method. The transit method is when we're basically looking for a planet to pass in front of its star, and this is called a transit. And when it does, it partially dims the star, and this can be detected by extremely sensitive instruments. And so this is by far the most productive method yet. In fact, more than 4,000 planets around other stars have been discovered using the transit method. So we'll look at how that works in more detail shortly. And there's another method called the Doppler shift method that looks for the wobble of the host star, and that's been also fairly productive with several hundred new planets discovered. Let's start with the direct imaging method of finding an extrasolar planet. So as I mentioned, this method is very challenging from a technology standpoint because the star is so far away and it's so bright compared to the planets that it's very difficult. But here on this slide, you'll see some of the best images we have of extrasolar planets. So this one here is the star has a catalog number HR 8799, and it contains at least 4 planets that were discovered by the Keck telescope. So this is actually an infrared image. So it's looking for the heat or thermal patterns of these planets. Now the star in the center, it doesn't look like a star at all. It just looks like a blurry blob. And this is because they've tried to mask out the light of the star by placing a mask or a filter in front of the image of the star. And so all of this all of these effects that you see in this image here, those are all just defects in the image due to the glare of the star. But one thing that shows up for certain is the presence of 4 distinct planets. This one is very faint out here, that are glowing in the infrared. And we don't have any detail in this image. In other words, these blobs that we see here that are labeled B, C, E, and D, this is the position of where those planets are, but we're not actually seeing the planet that size. This just means it's giving off infrared light and it's creating a detection on the telescope detector there, but it clearly shows the presence of these planets. This is another example here from the Japanese Subaru telescope, which is another really large, it's an 8-meter diameter telescope. And this is a star in the constellation of Lyra that contains at least 2, maybe more, planets. And again, the star, you can see, is actually masked out here. This dark circle in the center is a mask they put over the star in the image. And all of this speckles and diffraction patterns here, this is all starlight that is sort of like polluting the image. But you can see these 2 little blips here that are circled, and these are 2 planets that are orbiting this star. And here, our last example here is another one. Here the star is plainly in view, and here is the tiny little planet out here that's orbiting the star. So this is about as good as we can get with today's technology of actually detecting planets around other stars. But I think it is really cool to be able to look at these images images and say that we are actually looking at planets orbiting another star. These are other solar systems that could be like our own. So far, the most productive method by far of finding planets is called the transit method. And there were a couple of missions called Kepler and TESS that were satellites that were sent up in orbit, and their sole purpose was to detect planets using the transit method. So what is a transit method? Well, here's a little animation that shows it very well. Let's say we have a star here that we're looking at in the sky. And let's say this star has a planet, and this planet is orbiting around and around the star. Well, if the orientation of this system is just by chance correct, so that this planet actually goes in front of the star, then this is like almost like a mini solar eclipse. Instead of the moon blocking out the light of the sun, it's this planet. But obviously this planet is not going to completely block out its star because the planet is much smaller than the star. So instead what we see is this is called a light curve. This is the brightness of this star over time, and notice it dips when the planet goes in front of it because the planet is blocking some of the star's light. So there's a tiny little dip in the intensity of the brightness of the star here, and it's a very tiny amount. It's a tiny fraction of a percent, and so this is not something that could be seen with our human eyes, but by using very sensitive instruments called a photometer, which measures the amount of light, it can detect these little blips. And so what the Kepler mission did, here's a picture of the satellite here, it monitored about 145,000 stars all at once. So in other words, it just pointed at a very busy part of the Milky Way galaxy where there were lots of stars visible, and it looked at this same region for about 4 years. And over time, whenever it would find a dip like this, it would flag that star, and it would look for, if it truly is a planet, then it should be a predictable dip every time the planet orbits the star. So they can have a high confidence that what they're actually seeing is a planet and not just some other random variation in the star's brightness. So using this method, the Kepler mission found over 4,000 extrasolar planets. So this is just an amazingly productive planetary finding mission. There's actually, the Kepler is pretty much done with its mission right now, but there was a follow-up mission called the Transiting Exoplanet Survey Satellite, or TESS. And it is the sort of new and improved version of Kepler that's going to continue this search for extrasolar planets, and the TESS scientists estimate or predict that TESS will find as many as 20,000 planets during its mission, which is happening right now. As I mentioned, the Kepler mission found over 4,000 exoplanets. One of the more interesting of its finds was basically 5 planets in one, in that it found a star here that actually had 5 discovered exoplanets orbiting around this tiny little star. And so this is sort of a miniature version of our own solar system. If we think about our solar system with the sun in the center, this is Mercury's orbit in here. This green region out here is the habitable zone, or the life zone of our sun. In other words, any planet that is inside of this green region here probably has the right temperatures to have liquid water. So we can see it with our solar system. Venus is sort of right on the inner edge. In fact, Venus is too hot basically to sustain liquid water. We think it probably had liquid water in its past. Notice Earth, is nice and well centered inside of our sun's habitable zone, as is Mars. And we think that Mars was once a wet warm planet as well. We'll talk about that later in this chapter. But the idea here is that in our solar system, we have at least one, and maybe you could argue 3 planets that are in the habitable zone. Well, in this version here, this Kepler 62 system, notice that there are also 2 planets here labeled 62F and 62E that are orbiting inside of this star's habitable zone, where the temperatures would be or could be just right to allow liquid water on the surface of these planets. So these kind of finds are very important because they tell us that there could be other Earth-like planets around stars. The next and last method we're going to talk about here of finding other planets or extrasolar planets around other stars is the Doppler method. And the idea here is that when a planet, which is the little white dot out here, is orbiting around its star or its sun, the sun actually wobbles. The 2 of them orbit around something called the center of mass of the system here. It's sort of like the balance point. So the planet obviously is moving much more, but you can see that the star is moving also. And so we may not be able to see this planet because it's so dim and too small and too far away to see. However, we can see the star very easily, and with a spectrograph, this star, since it's moving back and forth to our line of sight, it's going to produce a shift in the spectral lines. So remember earlier in the course we talked about the Doppler effect. When a source of waves is moving towards us, the frequency of the wave is higher, and when the source of waves is moving away from us, the frequency shifts lower. So this works, of course, with sound. Like when an ambulance siren is approaching us, we hear a higher pitch than after it goes away from us, and the pitch lowers. Well, the same thing happens with light. Light is a wave, and so it undergoes a Doppler shift. So when the star is wobbling towards us, towards the Earth, we see a blue shift. In other words, the spectral lines of the star are shifted towards the blue end of the spectrum. Conversely, when the star is wobbling away from us, okay, so remember, here's our Earth down here. Here's this star wobbling around in a circle, just like is shown up here. So this star is either coming towards us or away from us. And so when it's coming away from us, it produces a red shift. In other words, the spectral lines shift towards the red end of the spectrum. So what astronomers are looking for is when they look at the spectral lines of a star over a period of, say, several years, they watch for any back and forth motion of the spectral lines. And these back and forth motions indicate that this star is wobbling. And what makes a star wobble? Well, the only thing that can make it wobble like this is something orbiting it. So this is an indirect method of detecting planets around other stars. The first ever exoplanet was actually found using the Doppler method, and these data points here are showing the velocity of the star using the Doppler method, and you can see it fits very well to this line, which is the model. And this is the detection of the first planet, which was called 51 Pegasi, and this is the first ever extrasolar planet that was found around another star. So as of today, there are something like over 500 extrasolar planets that were detected using this Doppler method. This is a nice chart here. This shows a list of over 30 possible terrestrial-like planets. That means potentially Earth-like planets orbiting in their star's life zone. So what we mean by a terrestrial-like planet, since we don't know that much yet about the details of these extrasolar planets, but we do know things like the size and mass of the planet, and we also can figure out where the planet orbits around the star. So based on those things, if the planet is roughly Earth-sized, and if it's orbiting in the star's life zone. Remember, that's that ideal position around the star where it's not too hot and not too cold. Then these are potentially habitable exoplanets, meaning that there could be life as we know it on these planets. So this is kind of an exciting thing to make a list like this out of all those thousands of exoplanets. How many of them actually could support life? And these are so far our best candidates. Even though we have found quite a few planets so far, we're just really scratching the surface. The reason for this is that this is a diagram showing our Milky Way galaxy, which contains something like 200 billion stars. Our sun is located right around here in the galaxy, and we are only able to look out so far with our telescopes to find these other planets. So our planet hunting region is just a tiny little sliver or sample of the entire galaxy. And so all we're basically doing is taking a little sample and using statistics to try to estimate how many planets there actually are in the entire galaxy. And as our technology improves, we'll be able to extend the reach of our instruments and start looking farther and farther throughout our galaxy, to hunt for planets around more distant stars. So what is the total tally so far? Well, so far the number is over 4,300 extrasolar planets discovered, and this number is growing fast. There are more than 4,000 candidates. What that means is these are non-confirmed planets that we just need to collect more data before we can say for sure with confidence that it is indeed another planet. So you can see that this number 4,300 is going to grow probably exponentially as we keep looking for more and more planets. One thing we're learning is that the disks around new stars indicate that planet formation is very common. In other words, the number of planets probably outnumbers the stars. So if you think about just our Milky Way galaxy with something like 200 billion stars, there are probably several hundred billions of planets in our galaxy alone. And we'll talk about galaxies later, but our Milky Way galaxy is just one of more than 100 billion galaxies in the observable universe. So the numbers are staggering in terms of how many planets there could be in the universe. Now, the big question, of course, is how many of these planets are suitable for life? Well, we'll talk about this more in the last chapter of our course on astrobiology, which is the study of life on other worlds. One thing it's fun to speculate is how many Earth-like worlds could there be. As I mentioned, we'll look at this in a little more detail later in the course in the chapter on astrobiology. But just as sort of a teaser for that, based on the Kepler space mission data, which is, remember, a sample and allows us to make an estimate, there is an estimated 40 billion Earth-sized planets orbiting in the habitable zones of just Milky Way stars within our own galaxy. So imagine 40 billion Earth-like planets. Now, are they exactly like Earth? Almost certainly not. In fact, none of them may be exactly like the Earth. However, the odds here that some of them could be very Earth-like look like it's very high. To have this many potentially habitable Earth-sized planets, orbiting again in the right place around their star where there could be liquid water. So this is sort of a tantalizing number that suggests that life may be very common in our galaxy. But, so far, of course, we have not found it. Let's now return to our solar system after, seeing a good amount of evidence for other solar systems and planets. Let's take a look at our solar system and some of its properties. So the first thing we're going to look at here are the planetary orbits. So this is sort of a model of our solar system showing the sun in the center And all those little rings around the sun there are just the orbits of the inner planets, Mercury, Venus, Earth, and Mars. This sort of fuzzy-looking ring of debris between Mars and Jupiter is the asteroid belt, which we'll talk about later in this chapter. And then we have the outer planets. Here's Jupiter, here's Saturn's orbit, and then Uranus and Neptune. And then just for fun, we put Pluto's orbit shown here. So this is kind of what our solar system looks like in terms of the scale of how the planets are spread out. Now, there's a couple of very important features here that are not a coincidence. All of the planets shown here are orbiting or revolving around the sun in the same direction. So if we're looking at this model of our solar system from up above up above the North Pole, and we kept going out into space, we would notice that every object in this picture is rotating or revolving around the sun, orbiting the sun in the same direction, counterclockwise direction. Okay, and that is not a coincidence. The reason for that is all of these planets formed from the same solar nebula cloud. And remember, that cloud was rotating, so that initial rotation is preserved when the planets form. Otherwise, we would see random directions of the planets. All of the planets rotate on their axes in the same counterclockwise direction. All right. Now there is some exceptions. Uranus, for example, is knocked over on its side, we think due to a collision early in its history, but we're not sure. But the vast majority of planets are also orbiting on their axis. That's what makes the Earth's day, 24 hours, for example, in that same direction. And again, this is just preserving that initial rotational direction from the solar nebula cloud. And this is what we would expect from the solar nebula theory. The other thing is that you notice that the planets, let's ignore Pluto for just a little bit, but all of the 8 major planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, they all lie basically in a flat plane. In other words, you could set this model down on a table because it's kind of flat. So all of them have a very little tilt in reference to the solar system's disk. And so this is another indication that the planets formed from a flat disk. And remember, that's one of the key steps of the solar nebula theory is the formation of that flat disk. So these are all pieces of evidence that support this idea of the solar nebula theory. Our solar system, of course, is filled with planets, and we can basically classify the planets into 3 types. There are the inner planets, which are the so-called terrestrial or Earth-like planets. And we have to be careful, this word terrestrial or Earth-like, we have to be careful how we use that. The planets, Mercury and Venus are very different from the Earth, in a lot of ways. But they do share some common features, such as a rocky surface and very thin or no atmosphere. And so all of these inner planets share that type of geology. So these are Mercury, Venus, Earth, and Mars are the inner terrestrial planets of our solar system. The outer planets are called the Jovian planets, and Jovian is just Latin for Jupiter-like planets. And these are the gas giant planets. They're very different than the terrestrial planets. They're much larger, and also they're made almost entirely of gas, at least the outer portions of them are. So that makes their geology very different from the inner planets. And then we have a relatively new class of planets called the dwarf planets, which are made of ice and or rock. And Pluto is the most famous example there. Also, the asteroid Ceres is considered a dwarf planet, and they've discovered another planet called Eris, which is probably actually larger than Pluto, but it's found farther out in the solar system. And we'll look at these dwarf planets in a little more detail when we study the outer solar system in part 3 of this chapter. So let's take a look at the terrestrial planets in just a little more detail. This is a nice image here that shows the 4 terrestrial planets kind of all lined up so you can compare their sizes. This is Mercury here, and notice that Venus and Earth are very similar in size, and then Mars is the one on the right here. So these are the 4 innermost planets of the solar system. They're relatively small in size and mass compared to the outer planets. These are all dwarfed by the outer gas giant planets. They all have a high density, meaning they're made of solid material. They're not made of gas like Jupiter and Saturn are. They have a rocky surface or a crust, and they either have very little or relatively thin atmosphere. So even though we think of the Earth having a nice atmosphere that we can breathe, it's relatively thin compared to the thickness of our planet, and certainly is very thin compared to, for example, the atmosphere of the gas worlds like Jupiter, Saturn, Uranus, and Neptune. The other thing that these planets have in common is that none of the inner terrestrial planets have rings. They're basically too small, and they're too close to the sun to be able to have a system of rings. Now let's take a look at the Jovian planets. Remember, the word Jovian means Jupiter-like. The king of the planets, the largest planet in our solar system, is Jupiter. So the Jovian planets are sort of named after Jupiter. Jupiter, Saturn, and then the twin planets Uranus and Neptune are the 4 outer planets of our solar system. These are massive worlds. In fact, this little spot here on Jupiter, the Great Red Spot, it's a giant hurricane-like storm that's been on Jupiter for at least 400 years since we've been able to observe it. And this storm is larger than the entire planet Earth. So these planets are all of them are huge compared to our Earth. They have a much lower average density because much of the volume of this planet is made of gas. They all have very dense atmospheres. These are the gas giant planets. And interestingly, all 4 of these planets have rings. Now, you don't see the rings in these pictures, except, of course, magnificent Saturn here, but I'll show you later when we talk about the outer solar system. You'll get to see some pictures of the rings of Jupiter, rings of Uranus, and Neptune. The other thing that's very different about the Jovian planets is they all have multiple moons. In fact, we'll see that Jupiter has more than 70 moons. I need to update my numbers here. They keep finding more and more small moons. And the reason they have so many moons is that their enormous gravity was able to attract and capture a lot of small pieces of debris, which we call moons, to the planets. The other thing I'll mention here is that inside these planets, we're pretty sure there is a large solid core of rock and ice and harder elements. It's not gas all the way to the center, and these massive solid cores was able to attract a lot of gas during the formation of our solar system, and it's been able to retain that gas. And it turns out that this gas in the atmosphere of these planets is very similar to the gas that makes up our sun. So how do the planets actually form and grow? Well, we can do it in a series of steps, and we're going to look at that in the next couple of slides here. So the first step for the formation of a planet is at the atomic level, and this is just condensation, where you have atoms basically sticking together just the way water condenses on a cold glass of iced tea that's sitting on the table. And these condensations of tiny little atoms form dust grains, which create seeds for larger particle growth. And this next step is called accretion. So these small seeds that were created by condensation start to stick together or accrete. And once they do this, they form larger and larger particles until we reach the planetesimal stage. These are basically rocks and boulder-sized objects that are forming from these dust grains clumping together. And once this starts to happen, gravity starts to take over, and these larger objects start to attract more debris, and so they grow over time until finally a protoplanet is formed. And a protoplanet is the early stage of a planet's development. For example, the proto-Earth was a molten ball of magma. So you can think of this, oceans of lava basically in the early Earth before it cooled. So protoplanets are created from the collisions of all these planetesimals. So, the growth here starts basically at the microscopic level, and the particles, as they stick together, they grow and accumulate, they get bigger and bigger until eventually forming a planet. This slide shows sort of the later stages of the growth of a planet. So again, this first diagram here shows the planetesimals. You can think of the planetesimals again as rocks, boulders, things like that. So they're colliding, and the bigger ones are going to attract more objects because they have more gravity. So it's going to start to grow with time. They start to stick together and it grows. So over time we end up with a protoplanet gaining more and more material, and as this material falls in, it heats up the protoplanet. Remember that there's potential energy for all of these rocks and boulders that are slamming into the newly forming protoplanet. So this is a tremendous amount of gravitational potential energy that is ultimately converted into heat, into thermal energy. In fact, there's so much heat that this protoplanet heats up and actually melts. And once it melts, a process called differentiation takes place, where heavier elements like metals actually sink down to the center to form a heavy and higher density metallic core of the planet, and the lighter elements, like some of the lighter rocks, actually float to the surface. Also, because remember, this whole thing is heating up and melting, it's like molten magma basically. There is gas that outgasses from the rocks, and that gas bubbles up to the surface and is held to the planet by its gravity, and this creates the planet's first atmosphere. So the result, when all this is said and done, the result of this process called differentiation is we end up with a planet that has a metal core, a rocky crust around and mantle around the core, and around the outside on the surface is an atmosphere of gas. And of course, this is exactly what we see when we study our Earth's geology. We see these different layers of the Earth, including a core, a mantle, a crust, and an atmosphere. And all of this is explained by this sequence of growth, which is described here. The last stage in the formation of the solar system is the clearing stage, where the remaining debris of gas and dust is cleared away. And we don't need to get into the details of this, but basically the sun pushes out a lot of this debris, especially the lighter material like the dust and the gas. The radiation pressure from the sun, the actual sunlight, pushes against the gas molecules, and there's something called the solar wind of the sun, which is a flow or flux of particles coming from the sun's atmosphere, and this stuff is moving extremely fast, around 1,000,000 miles per hour, and it knocks against material and pushes everything away from the sun. There's also sweeping up of the larger chunks by the planets. So the planets act kind of like vacuum cleaners. The planet's gravity sucks up larger material, and especially during the early stages of our solar system, called the heavy bombardment period, roughly 4 billion years ago, there was a lot of cratering and collision of all this space debris. The skies were just filled with stuff falling to the Earth constantly, and we see the evidence for this still in the form of craters. This is a picture of our moon, of course, with craters, and then this is Mercury's surface here, which looks very much like the moon. It's just full of craters. And this is evidence from earlier in our solar system when there was more debris still floating around in the solar system. That debris has now been cleared, and our solar system is relatively clean of all this debris. So all of this clearing and cleaning took something like 100 million years. This is not anything that happened overnight. But during that, after that period of time of roughly 100 million years, there is no more material to make new planets, so planet building stopped relatively early in the history of our solar system. Remember, our solar system is 4.5 billion years old, so only during that first few 100 million years or so was there actually planet formation. After that, the planets were already made. So that is the end of part 1 of this video. We will continue on with part 2 next, and we'll look at the planets of the inner solar system, including our own Mother Earth.